Okay, finally, I want to touch on this banked roadway problem, banked curve. So be sure that you do your background work and your reading and videos, etc., for these banked curve problems before attempting this problem. It'll make a lot more sense to see this problem in the context of that other work. So this is a car, and imagine it's on a banked curve, banked racetrack, if you want to imagine it. So that's why I drew this top view up here so you could see that it's actually on a circular path, nice and simple there. And this problem actually poses two questions. And notice that our givens are coefficient of static friction, the radius of curvature, and beta, the angle of inclination. First of all, the question asks us, what is the maximum speed the car can have and still negotiate the turn? And then question B, which is down the page, asks, what is the minimum speed the car can have and still negotiate the turn? And when I'm talking about negotiating the turn, I mean at constant elevation. So the car is not going to slide up or slide down. So let's just talk through this physically for a second. If the car is going too fast, then the possibility would be for it to slide up the incline, right? Whereas if the car is going too slow, the possibility would be for it to slide down the incline. That might not feel intuitive at all to you, but that might make a little more sense once we unpack the forces. The reason that I'm talking about this is because you have to make a decision when you draw your free body diagram. And here up on top, I'm showing this force diagram. It's not a free body because it's drawn onto the physical scenario here, but you have to make a choice as far as what direction to make your force of static friction, because force of static friction is like a responsive force, right? So its direction will respond to the situations, one way to think about it. So when we're looking for the maximum speed in this particular part of the problem, what we need the force of static friction to do is to keep the car from sliding up the incline. To say that again, when we're looking at the maximum speed case, what we need the force of static friction to do is to keep us from sliding up the incline. So that's why I have it directed down the incline for this particular part here. You might have to spend a little bit more time on that and um, think about that a little bit more. Something else to keep your eye on here is remember the direction of acceleration. So if you're seeing an incline and automatically you start and you're like, okay, I'll rotate my coordinate system. Remember our motivation for rotating the coordinate system. Our motivation for rotating the coordinate system is to keep acceleration on axis. So if we're going to do that here, we wouldn't rotate our coordinate system because acceleration is actually in the horizontal here. It's pointing into the center of curvature. So, considering that, we don't want to change our coordinate system. We don't want to rotate our coordinate system. So, we will end up with a free body diagram that looks like the one shown here. Okay, so that usually is tough on students when they're used to every time I see an incline, I automatically rotate. But the reason I throw problems like this in here is because you need to learn how to solve this kind of problem. And also to make sure that you're not on autopilot, that whenever you see anything that's like a wedge or incline, you don't automatically think that that means rotating a coordinate system. We choose to rotate a coordinate system in response to the direction of acceleration, not just to the presence of an incline in the problem. Okay, rest of the details are in the written solution, so have at it and be sure that you work both variations of this problem.